So this video is going to cover virtual work for trusses. In this example, we want to find the vertical displacement of joint B, right there, if member EC, this guy, is 1.5 inches too short. Now, since this truss has an applied load to it, we're going to have to solve for both the vertical displacement of joint B due to force, and since it also has a little shortage on the design of EC, we're going to also have to find fabrication error. So the numbers that you see, the ones that are in purple, are going to be the calculated values for the member forces with the loads given. And the numbers in green are the applied forces here, and then also in green is the lengths of the truss that we were also given. The rest of it we have to calculate on our own. We know that A, the cross-sectional area for every single member in this truss, is 3 inches squared, and E is 29,000 KSI. So to start with, we need to unload our truss. And then we need to apply a virtual load at the point that we want to find deflection. And we said that point was B. And we said we want vertical deflection, so we're going to put a vertical load of 1 at joint B. Now we need to go through and find all of our member forces and member lengths. So to start with, let's find some zero force members. So if you look at joint A, you see that we have 2 members, and it really doesn't matter what the angle was. So these 2 members are also zero force. Then if we scoot our way over to B now, knowing that AB doesn't exist, you have 2 forces, or 2 members. We have BE and we have BC, but we do have an external load. So BE, if we sum the forces vertically, BE is going to be 1 in compression, and BC, if we sum the forces horizontally, is 0. So it's always good to start off by finding our zero force members first. Now if we can't do that, that's okay. We'll just go through each of the joints individually and find out which ones are and are not zero force members. So now that we have 4 members already solved for, we need to get our remaining 3. So to do this, we're going to start by actually finding our reaction forces. We have dx here, we have cx, and we have cy. So to start with, if we just sum the forces in the y direction and set it equal to 0, we're going to find that we have the 1 load going down at B and cy. So cy is equal to 1. So we can go ahead and write that over here. Next, we can sum the moments about C and set it equal to 0, taking counterclockwise to be positive. And we've got our unit load of 1. He's going to be going this way around C, that's positive, times his distance of 16 feet. Then we have dx. dx is going to go this way around. That's going to be negative. So negative dx times his distance of 24 feet. And those are the only forces that are going to act at C. So dx is equal to 0.667. And he is a positive number, so the value at the direction that we assumed is correct. So this is 0.667. Next, we can sum the forces in the x direction and set that equal to 0. and we've got negative CX, and we have minus DX as well, which is 0.667. So CX is negative 0.667, and the negative sign means we drew it in the wrong direction. So CX is actually going that way, 0.667. Now what we need to do is find all of our member forces. So maybe we should start by going down to joint D. Joint D looks pretty simple to me. So at joint D, let's draw it out. We've got a vertical member, we've got this member, and we've also got dx. So that's 0.667, and we have our force CD, and we have our force DE. Now, unfortunately, we might want to go through and start finding some angles. So we're going to find this angle here, this angle alpha. So what do we know about alpha? Well, if you look at the whole truss overall, you've got a side here of 24 and a really long side here of 16 plus 16, which is 32. And that's creating the triangle that alpha is in. So we're going to draw that out. So if we want to find the alpha angle, we said we've got alpha here, we have 32 and 24. So alpha is equal to the arctangent of the opposite, 32, over the adjacent, which is 24. So alpha is going to be 53.13 degrees. So maybe we'll write that up here. Alpha is equal to 53.13 degrees. Alrighty. Now that we have that, let's start solving for some forces. We can sum the forces in the x direction and set it equal to 0. We've got negative 0.667, and we have negative force DE. And since he is touching alpha there with the vertical, this is going to be sine of alpha. So we're going to find that FDE is equal to negative 0.833. So we can write that up here into our little truss. So we said FDE is negative 0.833. Next, we can sum the forces in the y direction and set it equal to 0. So we have FCD going positive, and we also have FDE times the cosine of alpha also going positive. Even though FDE is actually a negative number, you're just going to plug in a negative there. So FCD is going to be 0.5. So we'll go write him in. So we have 0.5 for FCD. Next, I'm going to go on to joint C because I already know 2 out of the 3 members there. One of which is a 0 force, and that's really nice. So on to joint C. So at joint C, we have our horizontal, we have our vertical, and we have our one force coming off this way. We've also got CY, which we said CY was 1. Let's just go ahead and leave just the number there. CY is 1. And we said we had CX, who is 0.667. Now we just found force CD. So he was up here, 0.5. We have this force, which is BC. And as you might recall, he was a zero force member, so that makes things exciting for us. And then we have force CE. Now we might want to figure out some angles. Some angles would be pretty cool, so let's go up and see what we can do. So what can we do? Well, I think an easy one to be able to find would be this guy right here. The reason I say that is because we can look at this right angle, this right triangle right here. Okay, well we have one side and that's 16. It'd be kind of nice to find everything else. So we can find those other values by using similar triangles. So let's do that. We've got the overall height here is 24. And we've got 16 and 16. So the overall is 32. And if I want to find this distance here, the height of, or the length really of BE, that's just similar triangles. So 24 is to 32 as our y distance is to 16. So y is going to be 12. So while we're at it, why not let's just go through and put some more distances in. We'll just leave it in this green color. So we've got 12 here. That's nice. And then if we try and find the hypotenuse, let's call this h. The hypotenuse of this wonderful triangle, we know that h squared is equal to 16 squared plus 12 squared. So h, the hypotenuse there, is going to be equal to 20. So this guy is 20. Let's put him on the top. Alrighty. Now, if that's 20, and this is the same triangle over here flipped, then this is also 20. That's good. And if I just kind of draw in a little dashed line here, and this distance was 12 down here at the bottom, and the horizontal is 16, well, that's the same triangle as well, so that's 20. So I just found all the lengths of all the members. That's good. That's information we'll need. But now let's go back and try and find our beta angle. So for beta, who is this guy right here, we have 12 and 16 and 20. Pick your whatever favorite you want to do. So the arctangent of the opposite, which is 12 over the adjacent of 16, that's going to be beta. So beta is equal to 36.87 degrees. Alrighty, finally, let's go back and solve for some member forces. So if we sum the forces in the, doesn't really matter which direction you want to go, but I'm going to pick the one with less forces. We're going to do the x direction and set it equal to 0. BC is already a zero force member, so forget about him. We have positive 0.667 going in the positive x direction, and we have negative force CE, and he is touching that horizontal there, so that's going to be cosine of alpha. That's all that's going on. Really hard to make a mistake there. So we have FCE is equal to 0.833. So again, we can go back up here and mark him in. Same color as before. We have 0.833. Now we found all internal forces. We have found all lengths. So now we need to make a chart. So we're going to make a chart right over here. of all the information that we know. So we're going to start by making a chart of our members. So we have AB, BC, CD, DE, EA, BE, and EC. Then we have their force under the given load, and that's going to be in kips. And that's just based off of what we were given before. So those numbers in purple. So we're going to go in and fill out that chart. We'll keep it consistent with our colors here so that you know where they came from. So we have 26.6 repeating for AB. We have 26.6 repeating for BC. CD was 40. DE is negative 66.6 repeating. EA was negative 33.3 repeating. BE is negative 40. And EC is 33.3 repeating. Then we have our member force for our virtual load. He doesn't really have a unit there. And we found those forces are our pink ones here and our orange ones for our zero force ones. So updating our chart, AB was 0. BC was also 0. CD was 0.5. We have negative 0.833. Then 0. Then negative 1. And then a positive 0.833. Then we need our length. And this length, by the way, was in feet. So we're going to update it in our green color here. Again, good thing we found all those distances, all those lengths. So length AB is 16 feet. BC, also 16 feet. CD, 24 feet. Then DE, 20 feet. EA, 20 feet. BE, 12 feet. And EC, 20 feet. So that's all of the information in our chart. Next, what we're going to do is recall that our deflection equation is the sum of big N times little n times L over AE. Very similar to PL over AE. So we need to probably sum, or well, we're not summing yet. We're going to multiply N times L. So just going row, row, and row all the way over there. So we're going to get 0 and 0, 480, then 1111.111. I don't know how many decimals you want to go out to. We'll carry 3. We have another 0, then another 480, then 555 point, we'll carry it out to 3555. Now we're going to sum all that up, and we're going to find 2626. It's 2626.666, all that repeating. Cool, so that's that value. Then, as we see in our equation here, due to force, we have that sum, 2626.66, we're just going to round up to 7, over A, which recall we need A and E. A is 3 inches squared, E is 29,000 KSI. Watch our units here. So A is 3, this is inches squared. This value is actually in kip feet. So this is kip feet. That's 3 inches squared, also times 29,000 kips per square inch. That's what KSI stands for. So if we're looking at this, kips are going to cancel. Inches squared is going to cancel. We're going to be left with feet. Sounds lovely. So we're going to get 0.0302 feet. I don't think anybody really cares about how many feet this is going when it's a fraction of a foot. So multiply it by 12, get it to inches, we get 0.362 inches. And this is going down. That was our applied direction. Then we need the deflection due to fabrication error. And that equation is the sum of all the lengths, the shortened or extremely long lengths, times n. Well, there was only one member that was fabrication error, and that was EC. So we're looking at EC here. Into our chart, we're looking at EC. We're looking at this number right here. So we said it was 1.5 inches too short. So that's negative. And then we've also got N for him was 0.833. So that's going to be 1.25 inches. It is negative, so negative means going the wrong way, so that's vertical. So if we want to find the total vertical deflection of joint B, we need to add our fabrication error and our force. So fabrication error is 1.25 inches going up, and our force deflection is 0.362 inches going down. So in total, we're going to have 0.888 inches of vertical deflection going up.